Now I have a pleasure to introduce our speaker. Dylan Vasey is a PhD candidate in the Department of Earth and Planetary Sciences at the University of California, Davis. His research focuses on the creation, deformation, and destruction of the Earth's crust and mantle due to plate tectonic processes. He's particularly interested in the role that the closure of small ocean bases play in the formation of the mountainous ranges, and uses techniques including geologic field mapping, microscopic and chemical analysis of rocks, and computer modeling to better understand this process. Funding for this fellowship is provided by the U.S. Department of State Bureau of Education and Cultural Affairs, ECA, through a grant to the Council of American Overseas Research Centers, KEOR. Please join me in a round of virtual applause to welcome Mr. Vasey. Thank you, Dylan. Would now like to give floor to you. Please go ahead, and I will mute my computer, my microphone here. Thank you.
Great. Thank you so much for having me, and thank you to ARISC for all the support of my research. It's greatly appreciated. I'm going to go ahead and set up my screen here. We tested this earlier, so hopefully this will still work. Is the right part of this visible?
Yes.
Okay, cool. Yeah, so I'm going to talk a little bit about some geological research that I do in the Greater Caucasus Mountains that's related to oceans opening and closing and tectonic plate activity that ultimately is forming the spectacular mountain range that we see in Georgia and elsewhere today. So I've divided this talk up into sort of three broad parts, and I've tried to make this sort of a general audience talk in the sense that geology is sort of notorious for a lot of obscure jargon that is very hard to access if you don't work in the field. So I've tried to kind of ease us into that a little bit. So I want to start with an introduction to kind of plate tectonics and what I mean by that, and the setup for continental collision, which is a fundamental plate tectonics process in the Caucasus. Then I want to talk a little bit about some of the field work that my colleagues and I do in Georgia, looking for this particular tectonic feature called a suture. We were just there in September for about a month conducting some new research. The first time we've been back to the Caucasus region since 2017, so that was very exciting. And then finally, I want to talk a little bit about what we do back at laboratories in the United States with samples that we collect in the rock samples that we collect in the field in order to answer some of our scientific questions. So start with this kind of overview of the scientific motivation for what we're doing. I often like to talk about Earth as an engine. I know this provides some kind of context for what plate tectonics is and why it's important. So this is really kind of big scale, but fundamentally, if the Earth has a bunch of residual heat left over from its formation 4.5 billion years ago, and that heat is being dissipated. And that drives the convection cells in the Earth's mantle, which ultimately drive plate tectonics and a lot of other processes that make the planet what it is today. So just as a kind of basic reminder, a convection cell, right? If you think about a hot water kettle, you're heating the kettle from below. You heat up water at the bottom of the kettle. That water becomes more buoyant, and so it rises. Then as it's at the top of the kettle, it cools, and so it falls. And the result is that you get all that movement of water in a boiling kettle that you're probably used to seeing. The Earth is not really fundamentally different in a lot of ways. In fact, a friend yesterday, when I was showing her this talk, described it as a donut kettle. And this is a model of how mantle convection works. So the colors here are temperature, so things that are blue are colder, things that are red are hotter. And this is the surface of the Earth. This blank area is the core. And what you can see is that basically the same kind of thing happens. You have hot material near the core that rises to the surface. You have cold material at the surface that then falls back into the mantle. And so these processes are what fundamentally drive plate tectonics and formation of mountains and formation of oceans and all other kinds of things that we are interested in. So that's just kind of setting the broad stage here. Let's see if I can get this slide to move forward now. There we go. Okay, So kind of focusing in on the surface of the planet, which is our main interest, we sort of divide things into what we call the lithosphere and the asthenosphere. So the lithosphere, you're probably familiar maybe from kind of basic Earth science, that the Earth is divided into a crust and a mantle and a core. The lithosphere is what we call the crust of the Earth, and then also the uppermost mantle, and I'll get into why that's the case in a second. And then the rest of the mantle we call the asthenosphere. And the fundamental difference between those two things is that the lithosphere is cold enough that it behaves brittly. It's hard, it's rigid, and the asthenosphere is hot enough that it flows. It's kind of like silly putty. And so the lithosphere consists of these kind of rigid things that are floating on the top of a flowing material. It's all solid, by the way. There's this kind of misconception that the Earth kind of consists mostly of magma or liquid. Everything is solid for the most part, except for the outer core of the Earth and some minor places of melt. But you do have things that are actually flowing in the solid state, which is why I use silly putty as the kind of analogy here. And so fundamentally, going back to this idea of convection, you have these convection cells that take place in the asthenosphere, or the lower parts of the mantle, where you have material coming down, material coming up, and then you have these relatively thin lithospheric plates, which are the plates of plate tectonics that are floating along on the surface. And so we have some examples here using South America, for example, is a place where you have a plate going back down into the mantle because it's cold. And over in the middle of the Atlantic, you have places where, you know, material is uprising and you have new lithosphere being created. So the Earth itself is, divided into these rigid plates that all have big cracks in them, which are the boundaries between the plates. There are lots of little complications within this map, lots of little what we call microplates, but these are sort of the world's major tectonic plates. For the purposes of this talk, the thing we're really interested in is we're interested in the Eurasian plate over here, and then the Arabian plate here, because the Caucasus region lies up here, kind of a little bit in the interior of the Eurasian plate, but the mountains here are all forming because of a collision that's going on, interactions between the Arabian plate and the Eurasian plate. And so I've hinted at this a little bit already, but there are basically three different ways that the boundaries or the margins of plates can interact, depending on the relative motions of the plates, which depends on complicated ways that the convection cells behave in the mantle. So one is a divergent plate boundary. This is where you have two lithospheric plates that are moving apart. The result of this is actually that material from the mantle flows up to the surface of the Earth and creates new oceanic crust. This is what's going on in the middle of the world's major oceans, including the Atlantic, for example. You can have convergent margins where two plates are being pushed into each other. The result is that material from one plate gets dragged beneath material from another plate and goes back into the mantle. Those were those blue blobs going back down in that little convection model. And then the third is that you can have two plates slide past each other in what's called a transform fault. For those of us who are in California, the San Andreas Fault, which produces most of California's major earthquakes, is a major, an important type of this plate boundary. So in the Caucasus region, we're really interested in convergent margins because fundamentally that's what's going on. We have plate convergence overall between the Arabian and Eurasian plates. And that can fundamentally take two different forms. So when you have an ocean involved, you get a process that's called subduction. This is because the crust and lithosphere under an ocean is relatively thin and relatively dense. The result is that it can sink very easily. And by contrast, the crust of a continent is relatively thick and relatively buoyant, and so it's actually pretty hard to send back down into the mantle. So when you have an oceanic plate and a continental plate converging with one another, the result is that the dense, thin oceanic plate gets dragged underneath the continental plate and goes back down into the mantle. And this produces a bunch of really important processes. It's actually where some of the world's major hazards take place. So there's fluids coming off of this subducting slab, we call it, that causes melt in the mantle, that causes some of the world's most dangerous volcanoes. Again, for kind of us in the US, the Mount St. Helens eruption in the 80s is a prime example of a volcanic eruption resulting from this type of process. It also produces some of the world's biggest earthquakes. So if you hear on the news about earthquakes in the Pacific that have caused major tsunamis, these are almost always produced in these subduction zone settings. The areas around Japan or Indonesia, for example, are all subduction zones. But ultimately, what often happens is that you run out of ocean, right? So you're subducting the oceanic slab, you are closing an ocean, dragging oceanic lithosphere underneath a continent, but there might be another continent coming at some point. So the kind of classic example that people tend to know is the collision of India with Asia or Eurasia, which is ongoing. So, 50 million years or so, India would have been offshore from Asia. There was an ocean between India and the rest of Asia, or what's now the Tibetan Plateau. And that ocean was dragged down beneath, but then eventually India comes in. India is made of continental crust and lithosphere, so it's too buoyant to subduct. And the result is that instead of subduction continuing, the two lithospheric plates kind of crash into one another. And neither of them can go down, and the result is that you get lots of deformation in the plates that ultimately produces mountain ranges. So the Himalayas and the Tibetan Plateau are the result of this continent collision between two continents going on. And this is a lovely little animation of this process that I found the other day. So here's India coming in, the ocean closing, India hits Eurasia, subduction stops because this plate can't go down, but things kind of squish together and you form these really high mountain ranges. And in this case, also the plateau in Tibet. So you form this really high topography from the process of continental collision. So that's a lot about other places that are not the Caucasus, but ultimately the Caucasus region is also forming due to this process. So here's kind of a map of Eurasia. We were just talking about India and Eurasia colliding, right? Here's the Himalayan mountain front, and then here's the Tibetan Plateau resulting from that collision. But there's another major collision going on to the west between Arabia and Eurasia. And if you kind of look just grossly at the topography here, you can sort of see what's going on here. If we look at Anatolia, right, there are lots of mountains forming. If we look over towards Iran, we have mountains forming in the Zagros. And then we have mountains forming in Armenia, and the south, the most southernmost part of the Caucasus, but then also notably the really high topography of the Greater Caucasus Mountains. So all of these things are the result of Arabia colliding with Eurasia. These arrows here are kind of showing relative motions of different parts of the Arabian plate relative to Eurasia. So over in Anatolia, things are kind of squishing out away from the collision zone, whereas in the Caucasus, Arabian material is kind of coming head on at the Caucasus, creating the major mountain range here. And this is actually a relatively new paper that does a great job of visually summarizing some of the details of what's going on in the Arabia-Eurasia collision. So first, some reference points here. So one is that this orange, this is present-day Arabia. The kind of light pink here is present-day Eurasia. So like here's the outline of Iran, for example. Here's the Greater Caucasus. Here's the Lesser Caucasus, LC. And then this gray is the ocean called Neotethys that used to separate them. Another geologic convention, this MA, I'll refer to this a lot, so I want to make sure I introduce it. This is just a shorthand basically for saying millions of years ago. So 55 MA is 55 million years ago. This is the kind of scale we're talking about in plate tectonics. So 55 million years ago, there was an ocean between Arabia and Eurasia. There was also basically the Black Sea still existed. This BSB is the Black Sea Basin. This is the Caspian Sea Basin, CSB. But that basin actually extended into the Caucasus region. So this GCB is what's called the Greater Caucasus Basin. This opened back in the Jurassic, which is about 170 million years ago or so. That basin is now gone. And this is the reason why, is that Arabia eventually collides with the margin of Eurasia. And then as those continents continue to converge with each other, subduction can't happen. And so instead, subduction jumps northward into the Greater Caucasus Basin. and that basin starts to close. And so you get that basin closing as time goes on, and then eventually, very close to the present day, that basin completely closes, and what's today the Lesser Caucasus region has collided with the Greater Caucasus region, forming a lot of the mountains that we see today. So if that didn't make sense in map view, here's another look at it in a kind of profile view, or what we would call a cross-sectional view. So now we have Arabia, we have the south here and the north here. Here's Arabia, here's Eurasia, same set of time steps. And you can see too this process of subduction to collision. So we have Arabia moving towards Eurasia with subduction closing this Neotethys ocean. Then Arabia eventually comes in and hits. And the result is that there's still continued convergence. And so subduction instead jumps into this back arc basin, and we start to close this back arc basin. And then ultimately, we close the back arc basin, forming the present day Greater Caucasus and the Lesser Caucasus to the south. So this part of the system is ultimately what we're looking at in the Caucasus region. So in terms of what our research group is doing, we're kind of interested in the moment at a few sort of key questions. One of these is just basically finding, I'll kind of go back and look at this for a second, finding where the boundary is where this basin closed. So where is what we call in geologic terms the suture, coming from the medical idea of, you know, closing a wound and bringing stuff together, right? So this is where the two continents have been sewn together, so to speak. Finding the suture that marks where the Lesser Caucasus and the Greater Caucasus have collided. Finding out if that exists, and then finding out where it is. This is actually something that's not a trivial question in the Caucasus. There are other places where this is relatively straightforward to figure out, but in the Caucasus region, this is actually quite challenging because of the nature of the types of rocks that are exposed, and also how young, geologically speaking, the collision is. This is only something that's only happened in the last 5 to 10 million years, which for us is very, very young. And then ultimately, kind of looking forward, we want to understand how the processes that build mountain ranges and connect back to the larger Earth system are distributed to the north and the south of that suture, or that fundamental boundary. But the focus here for this, where we are in this study, is really just on locating the suture and determining if it exists and what marks it. So with that, we're going to kind of move into the second part of the talk here, which is what do we actually do when we go to Georgia to work in the Caucasus in the field. So I'm going to kind of just go through a lot of methods and field photos here just to kind of demystify what it is we actually do when we're wandering around in the country. So I mentioned that the suture is a kind of a non-trivial thing in the Caucasus, and the really fundamental problem is that we're missing a rock package that's called an ophiolite. Again, lots of jargon, but an ophiolite is really just a shorthand for saying a package of rocks that were originally formed as oceanic crust. So, and that are now on the continent today. So there's a number of different rock types in this. There's what are called pillow basalts that have this kind of circular look to them, sheeted dikes, gabbros, and then going down into these rocks that are broadly called periddotites, that are rocks from the actual mantle of the Earth. So places where the Earth's mantle has been brought up to the surface. This is considered kind of the diagnostic indicator of a suture, because if you're seeing ocean rocks that formed in an ocean on a continent, it means there had to be an ocean there before in order to bring them up on the continent today. I'll go ahead and just throw out there that this does not exist in the Caucasus. There's no nice ophiolite to mark this. And so we have to kind of look for some other indicators here. And we kind of take a three-pronged approach to finding other indications of suturing in the Caucasus region. The first of those is what we call sedimentary provenance. This is basically looking at sedimentary rocks that were deposited in the back arc basin on opposite sides of the basin, and asking, do we have some kind of indication that they were eroded, the source material, the sediment that formed them, came from different sources? So can we figure out that rocks on the south side of the suture were eroded from stuff on the south side of the basin, and rocks on the north were eroded from stuff on the north side? Or is it all kind of from the same source? Another thing is to look at the chemistry of volcanic rocks, of igneous rocks in the Caucasus. Basically, do volcanic rocks have chemical evidence when we look at them in detail that actually suggests they are part of oceanic crust? So really, this is another way of saying, is there actually an ophiolite, and we're just missing some of the key parts of it, but we can figure out that it's there using chemical techniques. And ultimately, something that's a little more kind of abstract in some ways is this idea of thermochronology, which is a way of giving an age for changes in temperature in a rock. And ultimately, temperature is related to the history of the rock as it's been involved in collision. And so if this is a fundamental boundary in the mountain range, we would think that maybe rocks on either side of it would have fundamentally different thermal histories or temperature histories that we can tease out using this technique. So we'll get into those a little bit towards the end. But for now, I want to talk more about what we do in the field. So this is a kind of just overview of the simplified basic geology of the Caucasus region. So we've rotated things a little bit. So note that north is not straight up. This is the Black Sea to the west, the Caspian Sea to the east. I don't have it on here, but the outline of Georgia, kind of goes something like that, right? So the kind of western central part of this, here's Tbilisi for reference. And broadly, we have this collision that I talked about between the Greater Caucasus to the north and the Lesser Caucasus to the south. And that back arc basin, the rocks that were originally in that basin that is closed are here in blue and in green to some degree. So we have all of those rocks that were formed at the bottom of the ocean that are now making up the kind of core of the mountain range itself. And our study area is in this red box, which these little white toothed things are major faults. So we are looking at the area where faults have formed as the mountains have been uplifted. So ultimately, we're working in the Georgian regions of Svaneti and Kazbegi. We have kind of three different profiles across the mountain range that we work in. Two are in Svaneti, one in kind of westernmost Svaneti. For those who are familiar with the region, Mestia lies kind of up in this little green sliver up here in the Svaneti region. And we have this other route that we're based out of the town of Sagari, which is in this little yellow blob of rocks here. And then ultimately we work in the Kazbegi region. This is along the Georgian military highway that runs from Tbilisi up to the Russian border, which is up near here. And a lot of what we do is just driving. So because we're trying to cover such large distances in a relatively short amount of time, we go around in a four-wheel drive vehicle and we try to find places where rocks that we are interested in are exposed along road cuts. Sometimes these are on major roads. Sometimes this involves going off-road quite a ways. So this is an example kind of up near Mount Ushba in Svaneti, where we got the car about as high up as we could go, after 40 minutes of off-road driving or so, and then hiked the rest of the way up to try to get to an outcrop near Mount Ushba. So we do a kind of a combination of driving around and hiking in order to get where we're going. I want to point out that we are really, really grateful for and dependent upon colleagues from Ilia State University in Georgia who come with us and work with us on this and are just great collaborators. As geologists who come to Georgia for a month every few years, we are not literate in Georgian by any means. And we don't live in the country for really long periods of time, and we're trying to travel a lot. So we're really dependent upon them for helping us out with language and logistical support and finding places to stay, and also for their expertise on the geology of the region. So just wanted to kind of really acknowledge how helpful they are, and every year they've been really great. I mean, this is a picture of me and Irakli Sirladze from 2016, the first time I came to Georgia. This is Georgi Boychenko from several years ago when he visited California in the United States, and we went out to the redwoods on the coast together. And then this is Salome Guguladze and Georgi Marabashvili, who were some of the people who were with us this year in 2022, helping us get around and do all kinds of crazy things that made no sense. So I just want to point out that we could not, there's no way we could get around without an enormous amount of assistance from them. So one of the fundamental things we do is we use geologic maps as our guide and sometimes make geologic maps. So these are just maps basically that show what rock types are distributed in different places in an area of interest. So this is a map from the Soviet era. These are sort of the kind of basic resources we have to work with. And it consists of a quad with some rock types drawn on it, a legend that tells you what each of these rocks are, a column describing different environments that these rocks are deposited in, and then a cross section showing you how these things are laid out in the subsurface of the Earth. It's a little bit hard to describe why maps are so important in a short amount of time, but the fundamental thing is that we would assume that rocks, sedimentary rocks at least, which are often what we're mapping, are formed originally as just horizontal packages, one on top of another. The reality on the ground is that they don't look like that anymore. And so any deviations from that have to be the result of some kind of deformation. And we're usually interested in that deformation. So this little cartoon diagram just kind of illustrates this idea that initially A, B, C, D, E, and F would have all been deposited flat, but at some point they got tilted, and then this, what we call an unconformity, formed on top of them, and then more flat stuff was deposited, G, H, I, J, K, and L. And then ultimately a fault here has gone through and offset all of those units. And if you were walking on a map or looking at the surface of the Earth, what you would actually see is you'd walk from K to J to I to H, and then suddenly you'd be in J again, K and L. And maybe out over here, you'd walk through F and E. So this stuff wouldn't make sense on the surface. And our job as geologists is to use the distribution of rocks and a kind of model of something like original horizontality to reconstruct what things actually, how things have moved and what that means for our story. So one of the things we sometimes do is actually, refine or make new maps in the field. This is a photo of me from 2017 attempting to make a map along the Georgian military highway. So I've got just a piece of paper with a topographic base map on it, and I'm looking around at the rocks around me and trying to mark what rock type is where. So part of what we do is field mapping. And then a big part of what we do is just collecting samples of different types of rocks. This year, we sent back a huge amount of rock to the United States, about 750 kilograms of rock, which was an enormous undertaking. But the reason we do that is because there are a number of things we can do back in the laboratory to make better sense of what the rock is telling us about the history of the Earth. So one thing we often do is we crush up the rocks. This is a lab facility basically just for destroying a rock, which is it's a weird experience to sit in a lab, clean it really carefully to prevent contamination, then smash up a rock and cover it in rock dust and then clean it again. It's kind of a funny thing to think about yourself doing. And then we break up the rock and try to extract different minerals from it. And oftentimes we can do laboratory analyses of these minerals to understand things like how old the rock is. We'll also cut up pieces of the rock to look at microscopically. So this is a photograph of what's called a thin section. This is this thing is a 30 micrometer thick slice of the rock that's so thin that we can actually have light pass through it in order to look at the optical properties of the various minerals in it. And this is an example of the kind of scale we look at. So the scale bar is about 1 millimeter. So we can actually look at individual mineral crystals that are, only a few micrometers and use their properties to observe features that would otherwise not be apparent in the rock if we were just looking at it at a hand sample. And then there's the question of how we actually get the rocks. We geologists, we always have to know exactly where the rock came from in order to put it in its proper context. So we can't pick up rocks out of rivers or on the ground and just take them, right? Because those rocks are what we call float. They could come from anywhere. I mean, they may have fallen off the mountain from relatively close, or they may have traveled quite a long distance down a river and we can't know the exact source, or a human could have dropped them there. That kind of thing happens too. So we have to take rocks from the actual outcrop, which can often be quite challenging. So we carry a variety of hammers and chisels with us. And, if it's something like a granite that's very hard, we have to kind of look for weaknesses in the rock and slowly extract things out. And then once we've gotten things out, we often have to break them down further in order to bag them up and take them with us. So there's a lot of time spent in the field just kind of hitting rocks with hammers, which is, again, one of these things that it's like, why am I doing this? This is a very strange experience to just be sitting around hitting a rock with a hammer. And then ultimately we have to get the rocks back to the United States, which itself is a sort of challenge, especially when you're dealing with 750 kilograms of rocks. So this is a photo of a bunch of we use these barrels that are normally used for making wine in Georgia. We buy them up and use them for shipping rocks, just because they're a nice size where if you fill them with rocks, you can still lift them. Basically anything bigger than this would be too heavy for a single person to move themselves. So we get a bunch of these, we take them down to a shipping service in Tbilisi. They're very confused by why we are doing this, and the idea too that the rocks have no monetary value. We're shipping this enormous quantity of material, but we're also claiming that it doesn't have any resale value. And then we get all that stuff back to the US in order to do the various laboratory analyses that we're interested in. So that's kind of just an overview of the fieldwork. Like I said, a lot of it is just going around and getting materials we need to do subsequent analyses. So I want to talk a little bit then about what we ultimately do on these rock samples in order to answer this question of where our suture might be in the Greater Caucasus region. So I talked earlier a little bit about this idea of sedimentary provenance. One of the really key ways we can do this is by looking at a mineral that is frequently found in sedimentary rocks called zircon. This bottom panel here it's a false color, but it's a way of looking at the internal structure of zircon crystals. And for reference, this is a scale bar that's 200 micrometers, so that's 0.2 millimeters. So these are basically sand grains. But we have facilities where we can separate out a bunch of these tiny little zircons, put them on a mount, and then shoot them with a laser. So all of these red and white spots are places where we shot these zircons with a laser in order to blast some material off of them. And then we can measure concentrations of uranium and lead in them to come up with a radioactive isotope age. And in a sedimentary rock, we'll get a bunch of different ages. We won't get all the same age. And that's because the zircons don't form in the sedimentary rock. They form in other rocks that are then eroded in order to make the sedimentary rock. So instead of looking at an individual age, we look at a whole set of ages and use that as a fingerprint for what was being eroded to form the rock. And this is a kind of nice cartoon example of what this might look like in California, where we have a few different sources: the Sierra Nevada batholith, which is all granite, and some sediments in the Great Valley and other basins. And basically, these curves are a way of showing the relative probability of getting a certain age. So we have the age on the x-axis here. And basically, it's like if you take a random zircon from the Sierra Nevada batholith, you're most likely to get an age of 90 million years ago, but you might also get an age of 150 or any of these other areas that are filled by the curve. And so if you have a rock and you don't know where it came from, you can get a distribution like this of ages and then compare it to these known sources in order to figure out ultimately where it came from. So in the Caucasus, this is ongoing work. We haven't totally solved this problem, but broadly speaking, we see a shift in zircon provenance from rocks that are kind of north of this set of red faults that we call the North Georgia Fault System, or NGFS, and rocks that are to the south of this fault system. And so we've in this figure, we've combined hundreds, or in some cases over 1,000 different zircons in order to make some of these curves. And we have these characteristic peaks that describe different areas. And the key thing here is just that the rocks in the north have some peaks that don't show up in rocks to the south, and vice versa. And then we have some samples that are sort of in the middle of the range that have a kind of mixture of those two sources, but we don't know exactly where that happens. And we also have some other issues that don't allow us to kind of solve this problem in total. So we need more data of this type in order to figure out if there's a real meaningful provenance shift across the range. So one of the things we did this summer, of course, was we collected lots and lots of samples of sedimentary rocks. So this is just an example of an outcrop where There's bedding in these rocks. If you look, you can maybe see that there are these planes that kind of go roughly in this orientation. So these are sediments that are deposited one on top of the other and then tilted. So we'll collect those rocks and then use them to do more of these, what we call detrital zircon analyses. The other major type of chemical or laboratory analysis we do are these geochemical or chemical signatures of volcanic rocks. Basically, if we crush up a volcanic rock and we look at different elements within it, that actually gives us some indication of the original source of the melt, of what was being melted to form the magma that then later on became this rock. There's a lot of little detail in here, but basically these are different types of basalts that form from melting different parts of either the mantle or the crust. And then these diagrams here have a bunch of different elements on them. So these are the rare earth elements and then some other trace elements that we get in these rocks. And we can look at the patterns, the shapes of these curves for these different elements and use them to distinguish source. So this one has a kind of little positive slope, where these ones have these negative slopes or a more pronounced negative slope, or these have these little anomalies where these two elements are lower than you would expect. So you can start to use that to sort of fingerprint where rocks come from. And one of the things we've already done is just gone back and looked at some old data and, fundamentally just kind of determined, prior to what some previous workers have thought, there's actually some good evidence that rocks from the Caucasus do have an oceanic affinity or were formed as oceanic crust. And it's really this kind of what we call a demorb or depleted mantle signature here, with this kind of shallow positive slope that is a good indication of that. But this is ongoing work, and this is all data that others have collected that we've just reanalyzed. So a major thing we were doing this summer is going back and really collecting a lot more samples of igneous rocks from the Caucasus, including in some cases these pillow basalts that again have this kind of rounded shape. Pillow basalts are an especially helpful indicator of potential oceanic affinity, because the reason you get that pillow shape is when you have volcanism that's underwater. So the fact that these form these pillows is because the lava has actually come up, erupted underwater, and cooled really quickly, creating that kind of rounded shape. It's a process we can observe in oceans today. So these rocks in the Caucasus definitely formed in a marine setting. The question is whether it's actually oceanic crust, which we need to kind of look at from a chemical perspective. And then finally, there's this thing I mentioned earlier called thermochronology. This is where we're dating cooling of the rocks. And really the fundamental thing is that temperature for a rock is a function of how deeply buried it is. So as you go deeper into the surface of the earth, you get temperatures increase. So a rock that's sitting 3 kilometers below the surface might actually be 75 degrees Celsius or so, as opposed to being roughly 0 degrees at the surface. And there are actually minerals where we can date radioisotopically, and the date we get is actually a function of cooling beneath a certain temperature. So if we took this rock and we suddenly eroded off this 3 kilometers and exposed that rock at the surface today, and we dated it using one of these systems, we would actually get an age of 10 million years ago, which isn't the age of the rock, but is the age of the cooling. And so that tells us something about the rock's history after it was formed. And just kind of as a summary of what we already know about the Caucasus region, this is, we have a couple different thermochronometers that date different temperatures. And basically they tell us that there's something going on across some of these same faults. So there's one system that's called apatite fission track. And we get, there's a young age that's been previously reported in this area, and then a much older age to the south, and that suggests that there's some kind of important boundary along some of these faults that lie between these samples. And then some of the work we've done is with a different system called zircon, uranium, thorium, helium, where we've discovered a lot of young ages in the northern part of the range. There's some variation, so there's a kind of older age here, maybe suggests something about this fault. But then to the south, we've found much older ages compared to in the north that suggests maybe a difference in history across, say, this fault. But again, this work is ongoing. There's a lot we still don't know about the variations in thermal history. So we've again collected a lot more samples this summer from the Caucasus, targeting rocks that we think will have the minerals that are appropriate for this type of analysis, like these granites, for example. And then our collaborator at the University of Michigan have a lab for measuring helium specifically that gives us some more information about this. So all of that kind of comes together and eventually hopefully gives us a clearer picture of processes like suturing in the Greater Caucasus. So we kind of went on a whirlwind tour of geology in the Caucasus there. So just to kind of sum everything up, ultimately, because of its location within the Arabia-Eurasia Collision, the Greater Caucasus is a really good natural laboratory for geologists in order to understand Earth processes like subduction and continental collision that are ultimately connected to these larger plate tectonic processes that are driving the cooling off of the Earth since its formation. As geologists, we go to places like Georgia and we conduct field mapping and sample collection in order to understand some of these processes. And there's work we do in the field to kind of get that started. And then ultimately we bring a lot of rock back and use various kinds of laboratory analyses to learn more about the history that those rocks are containing that might not be immediately apparent in the field. And that ultimately is helping us get more at understanding this very important process of continental collision. So with that, I thank you for your time and for listening, and thank you to Arisk.